Last time we saw how we can call functions in a smart contract from another smart contract. So let's say I have this contract here. This is King of the Ether Throne. And I'm just going to create another contract. Let's call this one my contract. And in this one, I just want to call, let's say, the depose function in the previous contract. Now, we talked about this and we said that generally the different instances of the same contract are different, right? So whenever you deploy a contract on the blockchain, you get a new instance of this contract. And this instance is completely detached from all the other instances of the same contract. Okay. So if I want to call a function of this contract in this one, let's say I have another function here. Let's say it's f and it's public. And let's say that I want to call this function depose. So first of all, I have to know the address of the previous contract. So let's say I have an address, let's call it A. And then we saw that I have to basically write something like this. I have to use the contract name as my type name. So I say this, let's call it my KOE, basically becomes the King of the Ether Throne contract at that particular address. Okay. And then I could say my KOE dot depose, for example. Okay. So this was how I called functions in other contexts. So when we wanted to actually do this, I would first have to deploy this contract and then get its address and then give the address to the second contract when I'm calling the function f so that it can actually call the function depose at the correct address. Now, this presents us with a very obvious problem. And the problem is, what if I don't have the code of the first contract? So right now, I'm just compiling both contracts together, right? I've written both of them in the same Solidity file. So of course, when I'm using, for example, a reference to the function depose here, my compiler knows what type this function is. And if this function took some parameters, let's say if it took some value x, then my compiler already knows that I need to give a value x and it gives me a compiler error if I don't, right? And here, let's say I give 25 for x. But in general, this is not going to work because maybe someone else has written the code of the first contract and it's already implemented, it's already deployed on the blockchain, and now you just want to interact with it. You just want to write a new contract that interacts with contracts that are on the blockchain. You don't necessarily have the code of this previous contract because maybe this previous contract was not even written in Solidity, maybe it was written in some other language and only the bytecode is on the blockchain. So how would you actually call it? So if we go on Solidity by example, by the way, this is a great website. Use this for all of your projects and everything. So we can see how we can call a function. This is generally the way that it works. So let's say I have a contract. In this case, it's called receiver, and it has some particular function. This is the function foo. It takes a string, it takes a uint x. Now, if I want to call it in general without actually having it at compile time, this is how I can do it. I can first have the address of that contract. I always need the address. This is just like before. All I'm saying is that now I have the address, but I don't have the source code, right? So here's what I can do. I can say, I can use this address to actually call the function. So I can write address.call. And whenever I'm making a call, I can first of all set two different things. I can set the value and the gas. So what is the value? The value is basically the amount of money that I'm paying when I'm calling this function. So we've seen before that if some functions are payable, when we call them, we can also transfer some money to the contract that contains that function at the same time as the function call. So this is all that's happening here. Basically, this contract is calling a function in this previous contract, but it doesn't know that it's in this contract. It just knows that it's the contract at this address. And it's saying, when I'm doing this call, send this much money, attach this much ether. And also you can set a gas limit, because maybe when this function test called foo was called, it was given some amount of gas. Maybe it doesn't want to share all of its gas with this function, right? So maybe it wants to call the other function and just give half of the gas to that function. And if you don't set a value for the gas, it would just share all the gas that you have. If you don't set a value for value, it would set it to 0, so it will not transfer anymore. And the interesting part is this part. So I'm saying I want to call a function at the contract that is at this address, and now this is the name of the function that I want to call. Okay? So I say I want to call the function foo, but the name of the function also includes the signature of the function. So I say I want to call the function foo that takes a string and an uint 256, right? And then I have to include the parameters that I want to pass. So in this case, I want to say my string is going to be this string called foo, and my unsigned integer is going to be this one. Okay, and then there is some more tinkering here. You have to do like ABI that encode with signature. This is basically so that when you call a function, the called function knows who msg.sender is, basically who's calling it, and so on. So generally, this is how you call a function. And the interesting point is that call gives you two different things. It gives you a Boolean value, which just says whether the call was successful or not. So if the call is unsuccessful, if, I don't know, for example, let's say the function you called runs out of gas, or it throws an exception, there is a requirement that is not satisfied, something like that, then this Boolean would be false. And then this data is basically all the return data of that function. And very interestingly, this is returned to you as a bunch of bytes. So if this function that you were calling, for example, this foo, as you see here, it's returning a uint256, but you don't know it here. Here, all you know is that you're getting a bunch of bytes. So you have to convert these things manually. So generally speaking, it's very painful to call functions if you don't know the source code of the actual contract that you're calling, because you have to be very careful about how you call it. And then when you get the return value, you have to do the typecasting yourself. You have to convert it to the correct type. And of course, all sorts of catastrophes can happen if you have any kind of error here. So for example, imagine if I'm calling this function and I have any kind of error in writing this function name. And this can be like a typo. Maybe I put 1 O instead of 2 O's. But it can also be much simpler things. Maybe I put some extra space somewhere, right? Even an extra space would break it, and then it will not call the correct function. And the thing here is that because the two contracts are not compiled at the same time, the compiler has no idea what the contract at this address looks like. So it's not going to give you any errors. It's just going to compile it. And then just at runtime, when you want to call that function, it doesn't work. Okay. Great. So this is how you can call functions if you don't have the code of the other contract. But again, just try not to do this. Do this only as a last resort. Like, as long as you're writing your own code, just compile everything together. Let the compiler check that you're not doing anything fishy, that you're doing the typecast correctly, and so on. So this is the way I prefer to call functions, but this is the general way to call functions. Okay. Now, I want to go back to one of the issues that we talked about in the last session. And this was the issue of transferring money. So at line 17 here, I'm just transferring the balance of this contract to an address which is called king. So I'm just saying king.transfer address this.balance. Now, we talked about this last time. We said, what happens if the king is itself a smart contract, right? So if the king is an externally owned account, if it's not a smart contract, the account will just receive the money, right? The balance of this externally owned account will just increase. But if it is a smart contract, so let's say I have a contract here, let me call this king contract. And let's say that it had a bunch of functions. It took part in this previous contract and it became king. So let's say that this address king is pointing to an instance of my king contract. And now let's say that this line 17 is being executed. So I'm transferring some money to king. We said that in these cases, the receive function of the king will be called, right? Now, in this case, I don't have a receive function. And because I don't have a receive function, when this transfer happens, the transfer tries to call the receive function of the king, but there is no such function. And because there is no such function, it just throws an exception. And when it throws an exception, this function depose also throws an exception, so everything gets reverted. Okay. Now, this is bad, because if you think about it, the whole point of this king of the ether throne was that I should be able to pay some extra money and depose the previous king, right? But now if the previous king is a contract, and if that contract doesn't have a receive function, I cannot depose it, because whenever I want to depose it, it tries to transfer the money, but that throws an exception, and then the entire transaction gets reverted. So the king always remains king, right? Okay. And we saw that we can also have a receive function, and maybe my receive function is somehow malicious. We saw this last time. So let's say I have a receive function that just says require 1 equals 0. This will have the same effect. So whenever someone tries to pay money to this contract, it will just throw an exception, and then the entire transaction gets reverted. Okay. So this is bad. So we prefer not to use transfer here. What can I use instead of transfer? Now, again, we can go to Solidity by example. And there is something, well, yeah, this one. Sending ether, transfer, send, and call. So there are 3 different ways that you can send ether to a contract. You can use transfer, and basically if you do transfer, it will call the receive function of that contract, and it will allocate 2,300 units of gas. And if the receive function does not exist, or if the receive function throws an error, then transfer also throws an error. Okay? But that's exactly what we didn't want to happen. So we have this option, send, which also allocates the same amount of gas, but instead of throwing an error, it just returns a Boolean. What does that mean? Well, it's just something like this. You see, I'm sending here, and I have a Boolean value. That's the return value of sent, which basically tells me whether it was successful or not. So if the contract that is receiving the money throws some exception for any reason, then this value will just be false. And then I can check this value in my own contract and decide what I want to do with it, right? So let's go here and let's change this to send. So I say king.send this value, and then I have a Boolean, let's call it sent, which is basically checking whether it was sent or not. Now I can say if sent is false, if for any reason sending was not successful, I can decide what to do. Now, maybe I decide that I just want to, let's say, throw an exception, or maybe I want to just ignore it. So I can just ignore it, doing nothing, and then I will not have the same attack as before, right? Because now I'm just saying I'm sending the money to the king. It's the king's responsibility to receive the money correctly. And if this contract doesn't receive the money correctly, I don't care. I'm not going to try again. Okay. So this makes sure that if you have an attacker like this, who's just saying that my receive function is throwing an exception, or who doesn't have a receive function at all, they're the ones who are going to lose the money. Okay, but of course you can also mimic what transfer does. You can just say require send. And if you do this, basically, if sending was unsuccessful, then the function depose will also throw an exception. Okay. But there is a bigger problem here. And the problem is the amount of gas that is allocated. So if you look here, both transfer and send allocate only a very tiny amount of gas to the receive function of the recipient. Okay. Now, this amount of gas is not enough to do almost anything. Like, it's really very little gas. Now, imagine again in this King of Ether throne that your king is another contract. Let's say your king is this one. And maybe it's not even malicious. But whenever the receive function is called, it just wants to do some bookkeeping, right? So let's say it wants to do some basic stuff. I don't know. It wants to keep track of how much money it has received from each person. Okay. So maybe it has, let's say, an array called received from, and it says received from msg.sender increases by msg.value. So it's just keeping track of how much money it has received from different people, right? By the way, we usually don't use arrays in Solidity. We just use mappings. Okay, so I would just have a mapping, and this is going to be, I forgot how to write mapping in Solidity, sorry. Let's just Google it. Yeah, the syntax is like this. So let's say I have a mapping from addresses to uint, and yeah, I'm going to call this received from. Okay, and let's say it's also public. Okay, so all this contract is doing is that it's keeping track of how much money it has received from anyone. And whenever someone sends some money and calls the receive function, basically it just updates that. So this is not an attacking contract. This is actually a very honest contract that is not doing anything suspicious, right? But the problem is that when I'm sending Ether using transfer or send, I'm allocating so little gas that even this runs out of gas. Okay, so there is not enough gas. 2300 is not enough gas to update the mapping. Now, what happens here? Well, basically, it's the same as if this contract was attacking us. Because when I'm sending this value to this king, assuming that the king is this king contract, it calls the receive function, and then the receive function runs out of gas. And running out of gas is an exception. So the receive function gets reverted, it throws an exception. If I had used transfer here, then depose would also throw an exception, but now I've used send, so send becomes false, and then I will throw an exception in line 18. Right? So actually, both send and transfer are terrible ways of sending money. You should never use send and transfer to send money unless you're sure that you're sending the money to an externally owned account. Because if I'm sending money to a contract, they will very likely run out of gas. So I would prefer to use them only when I'm sending to an externally owned account. Now, how can I be sure if something is an externally owned account, if an address is an externally owned account? Well, if, for example, instead of msg.sender, you always use tx.origin, you know that tx.origin is always an externally owned account. So if you're paying tx.origin, you can use transfer or send. But otherwise, you shouldn't use transfer or send. Okay, so how would I send money if I cannot use transfer and send? Well, actually with call, which is very weird again. So remember, I told you that when we are calling a function, it's really important that we get the name of the function correct. So if we have any kind of spelling error or anything in the name of the function, it wouldn't work. Now, what does it mean when I say it wouldn't work? Well, basically, it would call the default fallback function, right? So if I try to call a function and that function doesn't exist, it just calls the fallback function of the contract. And this was also the behavior when I send money to a contract and that contract doesn't have a receive function. It will just call its fallback function. And of course, if there is no fallback function, then that's an exception, right? So let's say I have a fallback function here. And now, if I send money to this contract, because it doesn't have a receive function, the fallback function will be called. But also, if I just try to call a function of this contract that doesn't exist, so I'm calling a function with a name that is not in this contract, it would just call the fallback function, right? So I can actually use this to transfer money to this contract. So I would call a function of this contract that does not exist. I would just call some random non-existent function and attach some money to it. And it will call the fallback function and give the money to it. And the good thing is that when I'm doing call, I can control how much gas I want to give, and I can control how much value in Ether I want to give. Okay? Remember here, so I can, when I'm doing this call, I can say how much value I want to attach and how much gas I want to allocate. So that's actually how I send money. So let's go back here to this part. So look, this is sending using transfer, which we see has a lot of errors and a lot of problems. This is sending using send. Again, this is not a great thing. This is sending using call. So look what's happening here. I'm using call. And what is the function that I'm calling? It's just the empty string. It's something that can definitely not be a function name. And so it just calls the fallback function. And I'm giving it this much value, so it's just transferring this much value there. And I get to also set how much gas I want to allocate. In this case, I'm not saying anything about the gas, so I'm allocating all of my gas. So this is actually how you should send money in all of your contracts. So instead of doing this, instead of sending the balance to King using send, I'm just going to call a function of the King. Okay. So I'm just going to say king.call, and then I'm going to give it whatever value I wanted to give. So this was address this.balance, right? And then I'm saying call the empty function that doesn't exist. Okay. Now, what happens in this case? Well, in this case, I try to call the empty function. It doesn't exist, so it calls the fallback function of the King contract. But now I haven't allocated just 2,300 units of gas. I have given it all of my gas. So this part doesn't run out of gas. So the execution of the fallback function terminates successfully, which means that this Boolean value here would be true. And then I have successfully transferred my money. Okay. So again, in all of your exercises and final exam and like final project, I expect you to transfer money using call. Don't use the other ways of transfer. Okay, nice. Now I want to just show you some more attacks. Let's create another contract here. I'm going to create a contract called bank. And this is kind of a stupid contract because all it can do is hold your money for you. So it just works like a bank. You can transfer money to it. It keeps the money in your name and you can take it out whenever you want. Okay. Now, this doesn't make much sense. But in practice, the way this works is instead of keeping ethers, maybe it keeps some other tokens or NFTs or whatever, right? But just to simplify, I'm going to create a bank that keeps ethers. Okay, so I'm going to have, again, a mapping from addresses to, let's say, uint. And this is the amount of money that different people have deposited. So I don't know, let's call it deposit. So deposit of an address is the amount of money that that address has put into my bank contract. Okay. Now I'm going to also have a deposit function, or I can just use my fallback function for that. So let's say I have my fallback function. It's, sorry, it cannot be public. It's external and payable. And basically all it does is that it's called when someone tries to pay money to the bank, and it increases their deposit. So the deposit of whoever called this function increases by the value that they attached when they called this function. Okay. And then, of course, I want to have a function for withdrawal, right? So I have a function called withdraw, and let's say that it takes some X and it's public, it's not payable. So basically, if you want to take X units out, you would just call withdraw X. And again, our unit here is VA, which is like 10 to the power of minus 18 ether, whatever. Yeah. Okay. So I want to withdraw. Well, if I want to withdraw, I have to first check that the person who wants to withdraw has enough balance, right? So I'm going to require that the deposit of whoever is calling this function is at least X. Okay. And then I'm just going to transfer the money to them. But we said we're not going to use transfer or send, we're going to use call. Okay. So again, this is how I use call. So I have a Boolean, let's call it send, and I have some data, and this would be msg.sender.call, and then I'm just going to call nothing, but I'm going to give some value to it. Okay, the value is X. Okay, so all this is doing is it's sending msg.sender a value of X. And by the way, this works even if msg.sender is an externally owned account, if it's not a smart contract. Because if it's not a smart contract, it will just receive the money and there are no functions to be called. Okay. So I sent this money and that's it. And then I have to, of course, say that the deposit decreases. So the deposit of msg.sender decreases by this value X. Okay, so this is my withdrawal function. Let's say I want to also have some sort of an internal transfer function where someone can send money to someone else. Okay, I'm just implementing a bank. So I'm going to call this, I can't call it transfer because we already have transfer. Let's call it bank transfer. Okay, so here's the thing. I can say I want to transfer X units of money to some recipients. Okay. And I want to say this is also public. Now, again, I have to make sure that the sender actually has enough money. So let's say I save the sender as just sender so that I don't have to write msg.sender. And let's say that I also keep track of their deposits. So let's say sender deposits is, or I'm just going to call it SD, sender's deposit, is the deposit of the sender. And I'm going to have the deposit of the recipient. And then I'm just going to say require that the sender's deposit is at least X, because otherwise he cannot transfer X units. And then sender's deposit decreases by X, recipient's deposit increases by X, and then I write them back. Okay. Very simple bank transfer. Great. Now, what are the attacks that we can do on this contract? We've seen one of them before. And again, I wrote it like this because I want to emphasize that you should not write things like this. So the attack here is what happens if I transfer something to myself, right? So let's say that I'm some attacker and I have 1 Ether in this bank. So my deposit is 1 Ether. And then I call bank transfer and I say, I want to transfer 1 Ether to myself. So the recipient is the same as the sender. Now here, as you see, it checks that I have 1 Ether and I do. And then it sets SD to basically 0. It sets RD to 2. And then my deposit becomes 0. And then my deposit becomes 2. Because I'm also the recipient. So you see, there are these corner cases you have to be very careful about. So this is actually something that happened in a real smart contract. And someone stole like $500,000 based on this. So I have to also make sure that no one can transfer money to themselves, right? So I could just have something like this at the beginning, require that the recipient is not the same as the sender, right? Or I could just write this in a better way, right? So I could just write it something like this. I could say require that the sender has a deposit greater than or equal to X, and then first reduce the deposit of the sender without using any extra variables, and then increase the deposit of the recipients. Okay, and this will. Okay, but we have another attack here, which is actually the attack that was used in the famous DAO hack. And that's an attack on the withdraw function. So let's see what happens here. I call the function withdraw, and I'm giving it some value X. It first checks that I have enough money. It checks that my deposit is at least X. And if my deposit is X, it sends me X units of Ether or Pay. So it sends me X units of money. But the way this is sent is, of course, using call, because we saw that send and transfer have a lot of problems. But what does it actually do? Well, this call is going to call my fallback function. Now, let's say that I'm also a smart contract, because a smart contract can also take part in this contract, right? It can just send money and then its deposit will go up and so on. So let's say I have a contract called attack. And let's say that attack has already deposited some money in the bank. Okay, I'm not going to write those parts. You know how to write them. Now, here's the thing. Let's say I have some function here, f. So let's say function f, public. And I have also the address of the bank. So address B, let's say bank, my bank is a bank at address B. And then I'm calling my bank.withdraw. And let's say I'm withdrawing some amount. Let's say I had 10,000 in the bank already, and I'm also withdrawing from it. Okay, I have to also make it payable. Okay. Now, when I call this withdraw function, so if I call this f function, it will call the withdraw function of the bank. And then the withdraw function comes here. It knows how much money I want to withdraw. It checks that I have enough money. And then it sends the money to me using call. So it calls my fallback function. But now in my fallback function, I'm going to do something really cheeky. In my fallback function, I'm going to call withdraw again. So here, I'm just going to say my bank.withdraw, let's say 10,000 again. Now, I don't have my bank here, so I can just make it something like this. And then, okay. So, see what's happening here. It's actually very interesting. When I want to withdraw, this function checks my balance and then sends the money to me. And only afterwards, it's going to update my deposit. But when it sends the money, it calls my fallback function, which again calls the withdraw function. So this is before my deposit value is updated. So the withdraw function again checks that my deposit is X, and it is. So it pays again. And this goes on forever. Now, in this case, this is bad because we will just run out of gas. It's just an infinite recursive loop, right? But I could actually have a counter here. So let's say I have a counter, and every time I increase my counter and I say if the counter is, I don't know, at most 100, do this, right? So this makes sure that I'm paid 100 times instead of just once, right? And afterwards, of course, my deposit goes down, but who cares? I've been paid so many times, right? My deposit becomes negative. I mean, it's a UN, so it's an underflow, whatever. But the important point here is that I had, let's say, 10,000 units of money, and I could withdraw it 100 times instead of just once. I can even be better than this, and instead of just doing this, instead of checking how many times I'm withdrawing, I can just check the balance of the bank here so that I can take everything that was in the bank, right? So here, instead of saying that I have a counter and I just count how many times I'm withdrawing, I'm just going to do this. I'm just going to say if the balance of the bank, so if my bank.balance is more than this much. It has some compiler errors because you need the address, not the actual bank. So you need this B. So if B.balance is more than this. And again, I have to make the B public. I have to make it, sorry, global here. But you get the idea. So I can say as long as the bank has some money, I keep attacking it and it keeps paying me. So basically, no matter how much money I had deposited, I can empty the entire bank, right? Now, there are some limits to this. For example, you have a limit on the size of the stack. You cannot call too many recursive functions and so on. But you can do this attack anyway. Like, don't be too greedy. Just figure out exactly how much money you can take out and do it like that. And also, you get to choose the value of X. So if you can withdraw twice, you should just put half of the money of the bank in, and then you can withdraw all of it, right? So you have control over X. So this is called a reentrancy attack, and it's reentrancy because basically this function withdraw was called. It called the fallback function of this other contract, and that fallback function entered the withdraw function again. So it re-entered the withdraw function. And this was the source of the very famous DAO hack of 2016. Our internet connection doesn't work for some reason. Yeah, so you can read about this. It's a 4-minute read. So basically, in 2016, there was this really important smart contract called the DAO. It was one of the biggest smart contracts at the time, and it had tons of money in it, and it had this vulnerability. And someone basically stole the entire money of this contract, which was one of the biggest contracts. I think at the time it was something like 70 million US dollars, and it was a lot of money at the time. Nowadays, this is considered very small. But as a result of this, the Ethereum blockchain basically forked into two different currencies. There were people who said code is law, and they just followed the contract. They said that okay, this person has done a successful attack, but as the blockchain notes, we're not responsible for making sure that people cannot attack other people. If you were stupid and wrote a bad code, it's your problem. Code is law, we're going to follow it. And then there were other people who said that we cannot allow so much money to be stolen, so we're going to revert that transaction manually, and we're just going to create a different blockchain that doesn't have that transaction. And so this created two different cryptocurrencies. One of them, the one that did the reversion, is called Ethereum now. The other one is called Ethereum Classic. And the value of Ethereum went down by something like 90% at the time that this happened. And after that, there have been many other attacks like this, but there haven't been any forks. Everyone is just following the code is law principle. So if someone attacks your smart contract successfully and steals your money, no one's going to revert the blockchain for you. You've just lost the money. Okay. So this is reentrancy. You have to be very careful that all of your functions in your smart contract are immune to this kind of attack, to reentrancy. Generally, I've talked about a lot of different attacks in this course, and whenever you're writing a contract, you have to check that it's not vulnerable, at least to the attacks that I have taught you about. It might be vulnerable to other attacks. That's actually a very hard problem, like how to write a contract that no one can attack. There is no real way to do that. But okay, how do I actually stop this particular attack? How do I make sure that there is no reentrancy? Well, in this case, it's just a matter of reordering the code, right? So first, decrease the deposit and then send the money. And that would fix it, right? Because if the deposit is first decreased and then I send the money, and if this calls the fallback function, which again calls the withdraw function, so what? The deposit has already decreased. You cannot withdraw more than your deposit. That's one way of doing it. But a more general way is to just have a flag. So let's say I have a Boolean and I call this reentrancy flag, and it's originally false. So whenever I enter the withdraw function, I set this flag to true. Okay. And whenever I exit it, I set this flag to false. And here, I also require that this flag is false. So basically, the idea is that if I'm already in the withdraw function, and in any way I enter the withdraw function again, it will immediately violate this requirement, and it will throw an exception, right? So this makes sure that no one can do a reentrancy attack on you. Again, this is one of the funniest attacks you can think of. And it's actually amazing that people made money with this. So as you see, it's kind of hard to write good smart contracts because there are things that work in normal programming and you don't even think about it, but they don't work here. So for example, we had this bank transfer and we had to be very careful about corner cases. What happens if someone transfers money to themselves, right? And then we had this one here, we had this withdraw function, and we were just thinking about this line 15 as sending money to someone, but that's not what's actually happening. It's actually a function call. So we have to be very careful about these things. We have to be careful what exactly we're doing, and we cannot have any abstractions. We cannot think that, oh, this is just sending money. You have to be very careful. What exactly is it doing? And well, another way of avoiding reentrancy, which is not really recommended, is to use transfer or send, right? Because if you use transfer or send, there's not enough gas for reentrancy. But then you will have all the problems that I told you before. So actually, the correct way of sending money is to use to use call, and then have these reentrancy flags to make sure your contract is not reentrant. Okay. So as you see, sending a little bit of money is actually quite complicated business. Okay, we have 5 minutes. I don't really have time to cover anything else. I just want to tell you, go on Solidity by example and just watch all of their YouTube videos and look at everything here. Basically see all the examples, read all the attacks. there are many more attacks. Most of these attacks are not that successful. So you can look at these things. So there is reentrancy. There are problems when you have overflow or underflow. So you can imagine, for example, let's go here. And let's say when I'm doing this withdrawal, what am I actually doing? I'm checking that the deposit is enough, and then I'm paying the money and decreasing the deposits. Now, imagine if I didn't do it like this. Imagine if I just first decrease the deposit, okay, and okay, let's forget about all of this reentrancy business. Let's say I'm sending the money using transfer for now. Again, not recommended, but I just want to simplify it to show you another attack. So let's say this is my withdrawal function. It decreases the deposit by X and transfers the money. So I can also do something like this, right? I can say if deposit is greater than or equal to 0. Okay. So the idea here is that if you try to withdraw more than you have, you will just not get anything. Right. Now, what is the attack that I can do here? The attack is actually based on what happens when you have an overflow or underflow. Right. So this deposit, the deposit of MSG.sender, is an unsigned integer. Right. So let's say that my deposit is 0. And let's say that I want to withdraw 1 unit. What happens here is that my deposit becomes -1, right? And let's say this was an integer. So yeah, my deposit becomes -1. So it takes 0 minus 1, which is -1, but then it converts it to an unsigned integer. And if you convert -1 to an unsigned integer, and especially if you're using 2's complement, that gives you the biggest number that can be represented in an unsigned integer. It gives you 2 to the power of 256 minus 1. So your balance suddenly becomes 2 to the power of 256 minus 1, your deposit, and then you can again withdraw everything. So you have to be careful about these things as well. You have to make sure that you don't have overflow and underflow. There are other things here as well. We will talk about source of randomness, denial of service, and so on. But generally, just read about all of these hacks. The most important ones are reentrancy and source of randomness. We will talk about source of randomness next time. We've already talked about front running, but just read all of them and make sure you don't have any of these problems in your codes.